So I first want to thank Louise and Brady for the invitation. It's a real pleasure to be with you tonight here in your living room or kitchen or bathroom or whatever, wherever you are. So okay, so what I'm gonna talk today is black holes. So it's a really vast subject. And so I had to make some choices because there's lots of things to do. And I guess that you didn't want to spend 5 hours with me. So even though it will be fun. So I had to make some choices, and there is something that happened this year. So this year, the Nobel Prize in Physics was awarded in the field of black hole physics. So it was awarded to Roger Penrose, Reinhard Genzel, and Andrea Ghez for their work on black holes. More precisely, Roger Penrose got half of the prize for the discovery that black hole formation is a robust prediction of the general theory of relativity, while the other half was awarded to Genzel and Ghez for the discovery of a supermassive compact object at the center of our galaxy. So the objects lying at the center of this Nobel Prize, of course, are black holes. So black holes really are really a fascinating subject. So they are the most extreme, the most mysterious, but also the most paradoxical objects that lie in our universe. So since the Nobel Prize, since the Nobel Prize put them in the spotlight, I decided actually to try to explain to you the most I could do about black holes, but also tell you why these three people, Penrose, Genzel, and Ghez, got the Nobel Prize. Why? What did they do that got them the Nobel Prize? So the general framework to describe and understand black holes, the most we can do, is actually that of general relativity. So general relativity is a theory, so it's a theory that is due to Einstein. And it took actually 10 years to Einstein to work out the complete details of that theory. And for many people, it is the most beautiful and most elegant theory that has ever been written and that ever came out of a human mind. So it was invented in 1915, and actually exactly 100 years after the discovery of general relativity, it came again under the spotlight because of an observation, of a detection of something that GR, so GR is general relativity, had predicted. And that prediction, that was gravitational waves. So I'm going to say a little bit about them. So gravitational waves, they would be worth a whole talk by themselves, but so I'm just going to touch lightly about them at the end of the talk, because they're also related to black holes. So they were observed exactly 100 years after general relativity predicted them, and they got these three gentlemen here down there, so Rainer Weiss, Barry Barish, and Kip Thorne, the Nobel Prize for that discovery. So now, okay, to understand the basics of general relativity and how the theory came about and to put things in perspective, I will need to do a little excursion in the world of relativities. So there is a quiz question that I like to ask people when I give this kind of talk is, okay, so the question, who is the father of relativity? Now, from what we discussed, it's obvious that the father of relativity is Galileo. So that's the little joke, actually, that's a joke that you can find in Trivial Pursuit and these things. So the father of relativity actually is not Einstein, it's Galileo. And the type of relativity that he came about with in the 17th century is called Galilean relativity. And it's something that we are really, really familiar with. So the important statement about Galilean relativity is that velocities are never absolute. They are always relative. That means that the magnitude of velocity must always be appended by the phrase with respect to. So there is a simple experiment that we probably all experience in our lives. So imagine that you're sitting in a train in a station, and then the train starts going forward. And maybe you already had the impression that it was not the train going forward, but it was the platform going backwards. Maybe you had that impression. Well, that happens to me all the time. And that's just an illustration of Galilean relativity, the fact that you're completely, if the speed is exactly constant, you're completely unable to make the difference between you going forward or the platform going backward. So that's Galilean relativity. There is another thing about Galilean relativity, which is, imagine that you have a truck going at 50 kilometers per hour, and then you have someone sitting on the standing on the truck and throwing a ball at a speed of 90 kilometers per hour with respect to the truck. What will be the speed, the total speed of the ball for someone that's sitting on the sidewalk? Well, the total speed of the ball will just be the sum of the two speeds. It will be 50 plus 90 kilometers per hour. So someone sitting on the sidewalk will see the ball going at 140 kilometers per hour. And this is called Galileo's velocity addition formula. So this is something that we are pretty familiar with, something that is pretty intuitive. Now, okay, so that was in 1632. So now let's jump 250 years ahead. In 1861, Maxwell established the equations of the electromagnetic field. So that means that Maxwell was trying to understand the behavior of light. So he came up with a theory that was describing how light behaves like a wave. And he determined by computation what was the speed at which that wave should propagate. And what he found is something that you also probably heard about, is that the speed of light is 300,000 kilometers per second. So it's about 1 billion kilometers per hour. So that's damn fast. But what was really interesting about Maxwell equations is that what he determined is that the speed of light was 300,000 kilometers per second, regardless of the observer who measures it. That means that if you are on the sidewalk, or if you are on a truck going at any speed, the speed of light that you will measure will always be 300,000 kilometers per second, irrespective if you are moving or if you are not moving. C is the same for everybody. So this is what the Maxwell equations tell us. So now Einstein, at the end of 19th century, I mean, he learned about these theories. So he knew about Galileo's relativity, and then he learned about Maxwell theory. And he realized that these two theories, so Galilean theory and Maxwell theory, they are completely in contradiction. So on the one hand, we have Galilean relativity, for which speed, there is no such thing as an absolute speed. And then he had Maxwell equations, where c, the speed of light, is absolute, and it does not depend on the speed at which you're moving. And so this presented Einstein with a daunting dilemma. So he wanted to solve the contradiction, the blatant contradiction that exists between electromagnetism, Maxwell electromagnetism, and Galileo's relativity. And this actually, the resolution of this contradiction led Einstein to elaborate his first theory of relativity that's called special relativity. How did he solve the contradiction? Well, the contradiction is the following. He actually claimed that the one who was right was actually Maxwell. So Galileo was wrong and incomplete. So you cannot you cannot sum up velocities like this. For light, you cannot just sum up the velocities. For the speed of light, it's just going to be constant for whatever observer. So according to special relativity, the speed of light is a universal constant and is the same for all observers. A corollary of this is that nothing can travel faster than the speed of light. So that's a little bit strange, but actually the constancy of the speed of light does not appear completely, is not completely obvious from what I'm saying here, and we won't really need it, so I won't enter into the details. But the constancy of the speed of light has really profound implications on the structure of space and time. Why? Because what is a speed? A speed is just a space divided by a time. Speed is meters per second, kilometers per hour. So in a way, time and space, they have to conspire in such a way that the speed of light is always constant. So space and time, they are still different entities, but somehow they have to combine and they have to conspire in such a way that the speed of light is always constant. Also, space and time are no longer really independent. They're actually unified in a kind of structure that is called space-time. It's a bit abstract, but for now, all we need to know is space-time is a kind of stage on which all the events unfold. It's like a chessboard. You know, space-time is a chessboard, and on the chessboard, you have all the other phenomena that take place. So this is where we stand in 1905. So Einstein is happy because he has solved the contradiction between Galilean relativity and electromagnetism. And here we have some pattern that will repeat itself in the story that I will tell you today, is that it often happened in the history of sciences that sometimes you have two theories that are really working well in their regime of applicability, if you want. But when you try to combine them, there's something that goes wrong. And so this is one of my mentors, Andrew Stramenger, encapsulated in the slogan, contradiction leads to progress. So when you have two theories that seem to work, but they are in contradiction, when you try to unify them, when you try to make them work, you're sometimes led to build a new theory that solves a contradiction, and that sometimes leads to really groundbreaking developments and progress like special relativity here. Okay, so now we are in 1905, and Einstein is happy because he's 26, he's super young, and he has solved the contradiction between Galileo and Maxwell. But he was not happy yet, because he soon realized that his theory was incomplete. Why was it incomplete? Because it didn't capture gravity. So we all know what gravity is. Gravity is a force that makes apples fall on the floor, on the ground, makes the moon goes around the sun, the moon go around the Earth, and babies fall on the floor and they try to walk. So gravity is really a fundamental interaction. But special relativity does not include gravity. So at the beginning of the 20th century, gravity is described by something that you're probably familiar with and that you might remember from your high school, which is Newtonian gravity. So what does Newtonian gravity say is that when you have two masses, well, these two masses will attract. There's a certain force. What is the force? The force is just given in the middle of the slide. It's just the product of the two masses divided by the square of the distance between the two forces. So the further they are, the less intense is the force. And G, some constant, is Newton's constant. So gravity is the force that makes apples fall to the ground and makes the planets go around the sun. So Newton, he was a really cool guy. He was a really brilliant guy. So he not only did he find the universal law of gravitation, but he also wrote the laws of motion that you also might remember. You might remember the principle of inertia. The principle of inertia is that if you have a body, some marble that you put on a table, if there's no force acting on the marble, it will just stay there. It won't move. Or if you take a marble and you just throw it, if there is no force acting on it, I mean, what is the trajectory that it will follow? It will just follow a straight line at a constant speed, constant velocity. Okay, so that's called the principle of inertia. That's the first law of Newton. Then there is a second law of Newton. No, if you want to change the velocity of a body, you need to exert a force on it. So if you have a body and you exert a force on that body, that will give the body some acceleration. And what is the acceleration? It's just given by Newton's second law, which is the second equation there. So F is ma. So the force that you act with on a body is related to the acceleration of that body. Okay. Now the good thing is that the fun thing is that if you combine the laws of motion of Newton and the laws of gravity of gravitation of Newton, then you can find the trajectory that the body will follow if it's subject to the gravitational force of another body. For example, take the Earth. The Earth is supermassive. So it will act on the moon that has a smaller mass compared to the Earth. And you can compute what is the trajectory. You can compute using Newton's law what will be the trajectory of the moon around the Earth. You can do the same thing for the Earth around the sun. And what Newton's laws tell you is that the trajectory will be something that looks a little bit like a circle, but it's like a deformed circle. So it's going to be an ellipse, sorry. So the trajectory of the planets around the sun are described by ellipses. So like in blue, the blue curve there on the bottom right. Okay, but no, there is a big problem. So special relativity is incomplete because it doesn't have gravity, and gravity is described by Newton's theory. But then Einstein realized that it was a huge problem because Einstein's special relativity and Newton's theory, they are also in contradiction. So what is the contradiction between special relativity and Newton's theory? For this, I'll play a little video. So imagine that you have the planets going around the sun because there is the gravitational pull of the sun on the planets. Now imagine a cosmic catastrophe where the sun comes to disappear instantaneously. So if the sun disappears, well, the mass of the sun disappears, so the force acting on the planets disappears too. That means that instantaneously, what will be the trajectories of the planets? Well, they will stop following ellipses. The sun disappears. As soon as there's no force, they will just go on a straight line. Okay? But now the problem with that is that as soon as the sun disappears, instantaneously, the planets will just go on a straight line. But what is the speed of something that is instantaneous? Well, the speed of something that's instantaneous, that's infinity. And infinity is obviously bigger than the speed of light. So there is a big contradiction, is that Newton's gravity is in contradiction with special relativity because it allows for instantaneous propagation, something that is faster than the speed of light. So Einstein in 1905, he realizes this. He has worked hard to unify, to solve the contradiction between Maxwell and Galileo, and comes up with special relativity. And then he realized that gravity is described by Newton's theory, but these two theories are again in contradiction. So he had to sit back again and solve the contradiction. So special relativity was sort of easy, took him probably maybe a couple of months. But to solve that contradiction, it will take Einstein 10 years. I don't know if you can imagine working on the same thing for 10 years. And it culminated into what is called now the general theory of relativity, or general relativity. So what is this? The idea is amazingly simple. Okay, of course, when you know the answer, it's always simple. But what is a groundbreaking idea? So the idea is that gravity is not, for Einstein, gravity is no longer a force. Gravity is not a force that something exerts on something. In general relativity, gravity manifests itself through curvature, the curvature of space-time itself. What does it mean? So that means that in presence of matter, so to the left, we have the space-time in special relativity. So that's something that is flat and is just like some fixed, boring stage where nothing happens. Well, things happen there, but it's fixed. Now, what Einstein tells us is that gravity, in the presence of matter, space-time will become curved. So there is this image that people give, like it's a bit naive and it's not really precise, but you can imagine that you're holding a cloth and then you're putting some ball at the center of the cloth, and then the weight of the cloth will just curve it. And now what's completely crazy is that if you look at what are the straight lines in this geometry, so of course straight lines on a curved space, they are not straight in the sense that we can imagine them. So imagine that you have this cloth and you put some ball in the middle and it's going to be curved. You take a marble and you throw it there. So if you're far away from where it's curved, the marble will just go on a straight line, like on the left picture. But if you're close to the sun here, you will see that the marble, if you throw it really correctly with the right initial speed, you will see will start following a curve on that curve space, and that curve will actually be an ellipse. And that ellipse is the motion of, for example, planets around the sun. So we can be a little bit more precise. I don't want to bother you with too many equations, but still I wanted to show you. So how do we determine how space-time is curved? Well, this is determined by Einstein's equation. Einstein's equation is that's the white equation there. So we have two sides. On the left side, we have the geometry. We have the curvature, we have the cloth, and the exact shape of the cloth. That's captured by this object G mu nu. And on the right-hand side, we have all the matter and the energy and the mass content of the universe, or of the space-time you want to describe. So for example, for the picture in blue there, you will just put in the T mu nu, this orange object there, you would just put the mass of the sun, the object sun with its shape, its energy, and its mass. You will solve Einstein's equation and it will spit out for you the equation of that curve, of that blue grid there at the bottom of the slide. So there is a way to capture Einstein's equation. So what Einstein's equation are telling us, and what general relativity is telling us, is that actually matter tells space-time how to bend. So you give me the energy and the mass content, and the Einstein's equation will for you give you the shape of that grid underneath. And then once space-time, you have the shape of space-time, it will just tell you how matter will move. So, I throw this marble, it's a free marble on a curved space, and that will just describe some ellipse, and that's the motion, for example, of the Earth in the solar system. So now these equations, they seem extremely simple. It's just one line with a couple symbols. But that's really summary. I mean, these things, these objects, they have a lot of stuff in them. And actually, if you flesh them out, these Einstein's equations, they are second order differential equations that are nonlinear. So they are pretty hard to solve. They are really hard to solve. Okay. Okay, so general relativity is really nice. It gives us a really aesthetic way to interpret the gravitational interaction. And that's nice. But one question you could ask me is, okay, well, it's nice, it's elegant, but is it right? Sometimes it's a bit sad, but sometimes you have really beautiful theories. Like the Greeks, they had like crazy theories about the epicycles and all these things. And they were probably elegant, but they were completely wrong. So general relativity here, you can tell me, well, okay, that's elegant, gravity's curvature, well, nice, but is it right? So for example, Newton's theory was doing pretty well in describing gravity. So what is general relativity bringing me? So can general relativity explain things that Newton couldn't? And it's indeed the case. So there are a couple classic tests of general relativity. I'll just tell you one. So we know that planets, when they go around the sun, they describe this curve that's called that's an ellipse. Actually, it's not completely right. If you really look at certain planets going around the sun, the curve that they are describing is not a closed curve. So for example, if you look at Mercury, look at the orbit of Mercury, what you will see is that at every period, the orbit will start to shift. So Mercury will do, instead of just doing like this, it will do like this, and then it will start to shift and start to shift and start to shift. So every year, it shifts by a couple, I don't remember the exact value, but it's some minutes arcs per year. And so there is one effect. I mean, that effect we couldn't really reproduce using, I'm being a bit fast to be more precise. There are some effects we could explain, but some effects we couldn't explain just using Newtonian theory. So actually what Einstein did is that he took his theory and he computed the shift according to his theory, and he compared to the shift in Newton's theory. And what he found is that it was precisely general relativity that was right. The shift in the orbit of Mercury that was observed was explained by general relativity, while it was not explained by Newton's theory. So that was one of the tests that actually this crazy idea that gravity was not a force, but gravity is just a manifestation of curvature of space-time, that was one of the confirmations actually that idea could be the right one. So now there is other tests. Space-time is curved, so light rays are actually bent when they propagate in space-time. So that's one thing that can also be measured. There's another effect called gravitational time dilation. So also a crazy thing that if you are taking two watches, you put them at different places in a gravitational field. For example, you put one in the basement and one in the attic. Due to the fact that you are in a different height in the gravitational field of the Earth, time will not flow the same way. So it's a completely crazy effect. For those of you who have seen the movie Interstellar, there's also like a whole story to tell you there. But in the movie Interstellar, that's an important, crucial part in the narrative of the movie. Of course, on Earth, the time delay is small. It's tiny. It's like, I don't remember. It's probably something like 200 trillionths of a second per day. So there's no chance you will see this on your watch. But if you were close to a black hole where the gravitational field is much stronger, that effect can become dominant and important. Okay, so now remember that this whole idea of trying to find a new theory of gravity that came from the contradiction between special relativity and Newton's law. So how does interpreting gravity as a curved space-time, how does this solve this contradiction? Well, it can be seen in the following way. So now we will replay this cosmic catastrophe where we have the planets going around the sun and boom, instantaneously we destroy the sun. Okay, so let's play this.
If the sun disappeared.
So now if the sun disappears, what's going to happen is that the gravitational perturbation caused by the disappearance of the sun will actually propagate in space-time. So you see, we see these little ripples. So the gravitational perturbation will actually propagate in space-time a little bit like ripples at the surface of water. That means that it will take some time for the perturbation to get to the Earth, and it will take some time for the Earth to know that the sun has disappeared. Using Einstein's equation, you can actually measure, you can determine the speed at which that perturbation will propagate. And actually, it will propagate exactly at the speed of light. And that thing that we saw propagating just now, that has a name, and that is called gravitational waves. And this is exactly what was observed 5 years ago, and that got its discoverers the Nobel Prize. Okay, so in the case of the sun, I think it will take something like 8 minutes for the signal. So for example, if the sun disappears, you will keep seeing it for 8 minutes between the light, before the light of the sun gets to you, and the Earth will continue on its orbit for 8 minutes before it knows that it has to go on a straight line because there's nothing pulling it anymore. Okay, so contradiction leads to progress because now we have another entry in our table, in our table of contradictions. General relativity was born out of the contradiction between special relativity and the laws of Newton. Okay, so now we have all the tools to jump into the black hole. So, so what is a black hole? So first, let me give you like a naive idea of what a black hole is. So to put it, we can put it this way. So black holes are, sorry, I can see my slides. Sorry, give me a second. I'll just reduce this because otherwise I can't. Okay, so black holes are regions of space-time from which nothing, not even light, could escape. What do I mean by this? So if I'm standing on the Earth and I'm jumping or I'm throwing something in the air, well, of course, that thing will fall back on the Earth because there is a gravitational pull that will attract that thing on the Earth. But is this always the case? Well, no, it's not always the case because we know that when we launch rockets, well, the rocket, we just throw it in the air and then it just goes into orbit and just goes into the space or on the moon and doesn't fall back on the Earth. This is because there is such a thing that is called escape velocity. So now, so let's look at the cannon there, the cannon to the left of the slide. So if I throw a cannonball with some normal speed, not too big, well, the cannonball will fall back on the Earth like in A or B. But if I throw the cannonball at a sufficient speed, what will happen is that the cannonball will never fall on the Earth again. And even so, it can start orbiting the Earth. And if I throw it at a sufficient speed, like in E, well, the cannonball will just like go and fly away in interstellar space forever. So that means that when I throw stuff in the air, there is a limiting speed, and that speed is called escape velocity. That means that if I throw the stuff faster than that speed, then the thing will never come back and fall back on the Earth again. So for the Earth, escape velocity is something like 40,000 kilometers per hour. So there is no chance that you will throw something, it will never fall back on the Earth, but it's some finite speed. It's 40,000 kilometers per hour. And of course, that speed will depend on the mass of the planet on which you are. If you are on the moon, I mean, the mass of the moon, the attraction, gravitational attraction of the moon is smaller. So it will be just easier to throw a thing in outer space if you are on the moon. Now, imagine that you are on a star or on an object where the escape velocity is not 40,000 kilometers per hour, but imagine that that speed is the speed of light. Well, would we be able to see such an object? Well, why do we see objects. Why do we see the moon? Why do we see the sun? Well, we see it because the sun shines and light escapes from the surface of the sun and comes to our eyes. But now, what if you have a star or an object of which the escape velocity is bigger than the speed of light? Well, that just means that light will try to escape the surface of the sun or of the star and will just fall back on the star. So would we see such an object? Well, we won't be able to see it because no light would come out of that object. No, there is a condition that you can write such that the escape velocity would be bigger than the speed of light. So that condition, I just wrote it there. So if you have a star that has a radius r and a mass m, well, the escape velocity will be bigger than the speed of light if this condition is satisfied. So the radius has to be smaller than 2 times Newton's constant g times the mass divided by c squared, the speed of light squared. So just to give you an idea, so obviously the Earth is not a black hole. So the radius of the Earth is about 6,000 kilometers. So now take the mass of the Earth. What should be the radius of the Earth? What should be the radius of the Earth so that the Earth would become a black hole? Well, this is something we can compute. We know g, m, and we know c. Well, okay, oh yeah, so let me come back to this. So the quantity 2gm over c squared, this is a specific radius or a specific length that we will call the Schwarzschild radius for some reasons that will become obvious. So if r is smaller than the Schwarzschild radius of that body, it will become a black hole. It will be something that we won't be able to see from the outer space. So for the Earth, what is that radius? Well, that radius for the Earth is 9 millimeters. So the Earth would be a black hole if you manage to pack all of its mass. So that's, I don't know, 10 to the 24 kilos, 2 is 24 zeros. If you pack the whole mass of the Earth into a thimble. Well, I didn't know the name before tonight, so I had to check it out. But so if you pack the whole mass of the Earth into a thimble, then that would form a black hole. So now we realize that it's something that is really, really not usual. Okay, so stars that would have the same mass as the Earth, but like packed in 9 millimeters, that's not something that we expect to encounter really often in space. So that's the general idea of what a black hole is. But now, if we want to really understand what is a black hole and so how, I mean, if we really want to study them, the framework to study black holes is really that of general relativity that we introduced before. What is the story here? So in 1916, so a couple months after Einstein came up with his equation, the German physicist Karl Schwarzschild obtained the first exact solution to Einstein's equation. So he was a soldier, he was fighting on the Russian front, and still he found some time to solve Einstein's equation. And Einstein got a letter from him, and he was dazzled. He didn't believe it because, as I told you, Einstein's equations are super complicated. So even Einstein saw that it would take months and even years to find exact non-trivial solution to his equations. Because, I mean, no, that was the beginning of the 20th century. I mean, the computational power was not what it is now. We didn't have computers, we didn't have computer codes, and we didn't have the same computational power. So everything had to be done by hand. And solving Einstein's equation by hand, I can tell you, is really, really hard. So he found that solution. So how did he do? I mean, how did he do? It's super hard, it's super complicated equations. So what he did, actually he did what physicists love to do. When physicists are facing a computation that's too complicated, what they will do, they will beat it up and make it simpler. They won't solve the equations in the more complicated and more general solution. They will consider simplified situations. So what Schwarzschild did, he solved Einstein's equation. So he wanted to determine the geometry or the gravitational field outside of a star, but not any star. He looked at a really, really peculiar star, a star that is exactly spherically symmetric. So it's a sphere. So of course, there's no star in the universe that's exactly spherically symmetric. But using the symmetries, he was actually able to solve the equations just by assuming the symmetry. So what he did is, it's something that physicists call doing the spherical co-approximation. So, you have a co and it's really complicated, it's complete, super complicated shape. You just approximate it as a sphere. That's fine. For most purpose, it will be okay. So this is what Schwarzschild did. So he solved Einstein's equation and found the geometry outside of a completely perfectly spherical star of mass m and of radius r. Okay, so the Schwarzschild solution, what does it do? Well, it describes, in particular, planetary motion around the sun. So when you have a star for which the radius is bigger than the Schwarzschild radius, well, then it will just describe the nice grid that I have here. So you solve Einstein's equation, and we'll just give you the shape, that nice, like, weird shape. And then that's the space-time that describes the gravitational fields outside of the sun. So that's the case when the star in question has a radius that's bigger than the Schwarzschild radius. And as I told you, the Schwarzschild radius usually it's much, 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 much smaller than the radius of the star. For example, for the Earth is 9 millimeters. Of course, the radius of the Earth is bigger. For the sun, the Schwarzschild radius is 3 kilometers. So it's super small. The radius of the sun is 700,000 kilometers. So for most objects, for most stars, the geometry will be given by what you can see on your screen. But now, if you use Schwarzschild solution to describe an object for which the radius is smaller than the Schwarzschild radius, so imagine the mass of the Earth in something that's smaller than 9 millimeters, then the geometry will be drastically different. And the geometry that you will have when you have a star whose mass is compactified inside the Schwarzschild radius is given by this geometry. So we can see that this geometry is much more dramatic. We can see that this geometry at the center, at r equals 0, at the center of the geometry, there is something that seems to go completely wrong. It's like, it's like the tip of a cone. The geometry is not smooth anymore. Actually, space-time ceases to exist at r equals 0. And then there is another region. So what happens when we are exactly at the Schwarzschild radius, when r equals rs? So that's a surface that's called the event horizon. So there are two special points in that geometry. So let me describe these 2 points because they are really where the cool stuff happens. So at r equals 0, so the center of the black hole hosts what is called a singularity. So at r equals 0 here, at the tip of the geometry, everything breaks loose. The curvature becomes infinite. The gravitational force becomes infinite, and actually, general relativity altogether stops to be valid. Space-time ends there. Actually, we don't know what happens there. So that location is called the singularity. And now there is the other region. The other region is just at the location of the Schwarzschild radius. Oops. So that's here. So if you were to cross that region, nothing really special would happen to you. You would have, the only thing that would happen to you is that so if you are far from the black hole, far from the singularity, where the region is flat, well, there you don't feel anything. You would just feel cool, like in special relativity where there's no gravity. But as soon as you get closer to the object, closer to the center, r equals 0, you'll start entering into the throat and you will start feeling the curvature. They will still be fine. If you don't go too close to the surface r equals rs, you will still be fine. But as soon as you cross the horizon, if you try to communicate with the outer world, it's going to be impossible. And the reason is because of curvature. The path of light rays, it won't be able to go outside of the black hole. It will just like be trapped inside and end up on the singularity. So that surface, r equals rs, the Schwarzschild radius, that's called the event horizon. It's called the event horizon because nothing that happens inside that region, in the throat, in the throat at the bottom, nothing that happens there can have any effect on the outside of the black hole because nothing can communicate between that region and the outside. So the event horizon, that's the limit between these two regions. It's really like it's a one-way surface. You can enter it, but light cannot escape it. And of course you cannot escape it because you are slower than light. So you will never be able to escape it. Once you enter the black hole, you will probably still be fine, but you will never be able to tell your friends that you are fine. So there is this aquatic analogy. Imagine that you have a waterfall and you have where the water falls, called is a singularity. If you're far away from the waterfall, you're swimming and you can go and see, oh, there is a waterfall there. As long as you don't go too close, you can see there is something happening there over there. But if you are not too close, you can still swim back and dry yourself and have a beer. But if you go too close to the waterfall, if you cross the horizon, the stream will be so intense that if you try to swim against the stream, against the flow, you will still go backwards and you will still be attracted. And the only way and your future will be to fall in the singularity and fall in the waterfall because the attraction is so big that you cannot resist it. So that's a little bit the idea. If you were to enter a black hole, you will still be fine, like this guy swimming there, but your future will be determined. You will end up on the singularity where you will probably be destroyed. But we don't really know. Okay, so of course, the fact that there are spacetimes of black hole type as solution to Einstein's theory of relativity is not a proof in itself that black holes really exist. You have a lot of theories that have a lot of solutions, and you have to be sure that these solutions make any sense at all, right? So it's not because the solution exists that actually black holes in particular can, for example, form. If you are telling me that black holes exist, you need to tell me how they appeared. And so when Schwarzschild came up with a solution, it wasn't really understood what these solutions represented. It took a lot of time, at least 20 years, to understand this horizon thing. But then at the end of the 30s and beginning of the 40s, people started to understand a little bit better the formation, the birth, and the death of stars. And there it became apparent that black holes could be born from the death of stars. How does that work? So what is a star? Well, a star is a gigantic ball of plasma, of hot plasma that is burning. So essentially, the way a star forms, you have dust, and dust starts collapsing onto each other because of gravitational pull. And then as soon as the dust starts collapsing, the temperature raises. And you can raise a point where the matter at the center of the core of the star will start burning. You will start burning nuclear matter, and actually you will have fusion taking place. So hydrogen will burn into helium and so on. And so, of course, when something is burning, that tends to, there is some kind of radiation that tends to expel the matter outside, far away from the star. So a star actually hosts a permanent struggle between two opposite forces. There is the fact that there is something burning at the center of the star, and that tends to expel the matter. But on the other hand, all that matter tends to attract itself. The gravity is attractive. So on the other hand, we have gravity that tends to hold the layers together. So a star that is living, so during its lifetime, it's a really subtle balance between, the radiation pressure of stuff that it's burning, that tends to expel the layers, and gravity that holds the whole thing together. So people started in the 30s and 40s to understand how stars live and die. And what they realized is that, so when the star is done burning all its stuff, there is nothing to counteract gravitational interaction. Well, there can be stuff. So you can end up with a solid core that can counteract the gravitational pull. But if at the end of its life, the star is too massive, the internal pressure of the stuff that forms the star will just be too small to counteract the gravitational collapse. And what will happen is that the thing will start collapsing, and that will never stop. So that was studied by these three people, Tolman, Oppenheimer, and Volkov, at the end of the 30s. And so they came up with a maximal mass. For a maximal, a minimal mass, so that the thing will stop collapsing. And what they observed is that if the mass is bigger than 3 times the mass of the sun, then there is nothing that will prevent all that matter to collapse, and it will stop to, we don't really know, but we assume it will end up at a point where all the mass will be concentrated at one single point, which is a singularity. And so this is how in the 40s, by just understanding more stellar evolution, it just appeared that black holes can be born from the death of massive stars. So of course, a black hole is not the only end point, not the only possible end point of stellar evolution. So if the mass is not too big, so if the mass at the end is smaller than 1.4 solar masses, it will end up like a white dwarf. It's called a white dwarf. This is probably what will happen with the sun. And if it's slightly more massive, but still smaller than 3 solar masses, then the remnant of the stellar evolution will be a neutron star. Okay. So this is where we stand in the 40s. So in the 40s, we had 2 things. So we have the theoretical predictions that black holes could exist. So that was essentially Schwarzschild solution and the interpretation of Schwarzschild solution. And then in the 40s, people also came up with a mechanism to build, how to make a black hole. However, a lot of people believed that black holes could not exist. So in the 60s, actually after Einstein, so Einstein died in 55, and it is said that he himself didn't believe that black holes could exist. Actually, even he also interpreted the fact that the presence of a horizon and singularities like the fact that his theory was incomplete, that it would ruin his theory. So in the 60s, after Einstein's death, 5 years later, there was an intense debate. And a lot of physicists, they don't believe that black holes could exist. But then you could ask me the question, we have a mechanism, so we have a theoretical prediction that black holes should exist, that's Einstein's theory. We have a formation mechanism. What is the debate then? Well, why did people believe that black holes could not exist? And it's for the following reason. Is that what I just described, so the fact, the perfectly spherically symmetric star and the black hole formation that I just described by Oppenheimer, Volkov, and Thoma, it's really hard. It's a really hard computation, as I mentioned. So what they had to do to arrive at that conclusion, they had to make some assumptions. So in particular, they had to assume that the star was perfectly spherically symmetric. So what actually physicists believe is that the fact that the star would completely collapse into a singularity, they actually suspected that was an artifact of all the simplifying assumptions that we made, the spherical code. So this is what people believed at the time. So of course, real stars in the cosmos, they are never perfectly spherically symmetric. So what people believed back then, so the debate was, okay, spherically symmetric stars can form a black hole, whatever. Spherically symmetric stars never exist. Perfectly, exactly. So the question there was, could black holes form from a generic, completely symmetryless situation? So the question is, now if we have like a completely crazy star, are all these results still valid? Is it true that we will still form a black hole if we start with a real world star? And this is where we come to the first part of the Nobel Prize. So in '65, Roger Penrose, he's a mathematician. So he works in Cambridge, and he's a mathematician, but he's really, really interested in physics. So he hears about the problem. He hears about this big debate. So could black holes form from generic situations that are not spherically symmetric? So he hears about that problem from Wheeler, who's an American physicist, and he starts working on this. So the thing is that he developed a lot of tools. He used tools of differential topology. I mean, tools that physicists were not really used to use. And he develops a lot of tools to actually to address this question. And he ends up a couple months later, after having started to work on the paper, with a 3-page paper. That paper is really dense. So the question that he asked, so the question has been raised as to whether the singularity is a property of high symmetry assumed. So the matter collapses radially and warps to a single point. So that a resulting space-time catastrophe, there is perhaps, so the fact that there is a catastrophe is perhaps not surprising. So what he asked in his paper, could not the presence of perturbations which destroy the spherical symmetry alter the situation drastically? And his conclusion is the following: it will be shown that deviation from spherical symmetry cannot prevent space-time singularities from arising. So what he shows that even if the star, the original star, has no symmetry at all, the core will ineluctably form a singularity. I won't enter in the details of the paper, but that's what he did. So, so Penrose proved that within certain reasonable assumptions, like the energy has to be positive and other predictability conditions, as soon as you form a horizon, as soon as the star collapses and enters its Schwarzschild radius, it is impossible to prevent total collapse into a singularity within the framework of general relativity. So that's the reason why he got the Nobel Prize. And this is what they meant by the word robust prediction here in this slide. So Penrose, for the discovery that black hole formation is a robust prediction of the general theory of relativity. By this, they meant that it does not depend on the fact that you assume that the star was special, that it was spherically symmetric, that it was blue, red, or whatever. It is just some generic property that as soon as you have too much matter contracted in a sufficient radius, you will end up with a singularity where space-time will end and everything breaks loose. So now, just a little aside. So later, so Penrose at the time was something like, he was 34 years old. But later Penrose, he generalized these results to cosmology with a young PhD student who was 23 years old at the time. And it's not to process, to prove. And he applied his theorems to cosmology, not to black holes. And what he showed is that a singularity is also unavoidable at the beginning of the Big Bang model of the universe. So his theorems that he showed with this young PhD student, and this young PhD student, his name was Stephen Hawking. Actually, they showed that the universe had to start with a singularity. Then later, Hawking and Penrose started a collaboration where they generalized these theorems that are now known under the name of Hawking-Penrose singularity theorems. But this is how, this is what these theorems were about. Okay, so where do we stand now in 65? Well, we have three things. So Einstein's equation predict the existence of black holes. That's the one thing. Second thing, we know how they could form. They could form from the gravitational collapse of stars. And now the third thing is the third stone that Penrose and Hawking also brought is that these results, they do not depend on simplifying assumption. Generically, you will form a singularity. So in the 60s, now it became obvious what the next step would have to be. Well, the next step that would have to be taken was to try now to observe these objects. Because now, thanks to Penrose, people started to be convinced that these objects really existed. Okay, so black hole observation. What do you want to say? Well, let's see how we can observe black holes. Well, the first thing you can object to me, so well, how could we even observe black holes? Because they emit no light. Why are we seeing things? Well, I'm seeing you now because there's some light shining my screen, reflecting on the screen and getting to my eye, and this is why I can see you, why you can see me. But how could you ever see something that emits no light? So the one answer to that question is that because sometimes the black holes, they are betrayed by their surroundings. So one case where you can observe black holes is in binary systems. So imagine that you have a black hole, that's the yellow object there. Imagine that you have this yellow star there, but that's black and you don't see it. But we know that when you have some like massive object and you have some other object attracted by that object, well, it will follow a certain curve, and that curve is an ellipse. Okay, so if you have a black hole that you don't see, you might look in the skies and see something, some star that has a weird motion. It just doesn't go in straight line. It doesn't follow the galactic motion. It just seems to go something that we don't see. So how do we do this in practice? Well, we do this using the Doppler effect. So maybe you remember what the Doppler effect is. So the Doppler effect is the fact that a wave signal will have the wavelength of a signal that it will perceive will depend whether the thing that is emitting the signal is coming towards you or going away from you. You know, when there is an ambulance wailing, you hear something like I don't know if you see what I'm meaning. So the sound of the ambulance will change, the wavelength, the frequency of the sound. It will sound like with a lower frequency as the thing goes away from you. And it's the same thing with stars. So now imagine that you have a star circling something that you don't see. So the star will emit some light, but sometimes you will see that when the star comes towards you, well, the spectrum of the star will be shifted in one direction, and when the green star will go away from you, well, the spectrum will be shifted in the other direction, a little bit like the ambulance going towards you or going away from you. So sometimes you will see in the skies, stars of which, you know, the spectrum will periodically vary. And from this, even if you don't see the object around which that star is going around, you will be able to see, well, there must be something. That star is circling something. I'm not seeing it, but there must be something. Otherwise, that green star would not be doing that motion. And so the first such system, it's called Cygnus X1, that was discovered by these people in 1971. That's a binary system that is 6,700 light years away from the sun. That's somewhere in our galaxy. And now you observe that star. So in the bottom picture there, we don't see the capital M. All that we see is that we see little m going around in an ellipse. We don't know what is at the center. But no, what is nice is that using Kepler's law, now you observe the visible star. What you can measure the radius of the orbit. That's little a. You can measure the period of the orbit. That's capital T. Now using Kepler's law, Kepler's law tell us that a cubed over t squared is given by g times the m over 4 pi squared, and m is the mass of the massive object at the center. So just by looking at the orbit of the thing going around something that we don't see, we can deduce the mass of the object around which it goes. And for Cygnus X1, the mass of that completely invisible object, that could have been a neutron star. There are a lot of things that are really dark in the universe, but that thing, the mass of that thing is almost 15 solar masses, and 15 solar masses is much bigger than the upper bound that could exist for a neutron star that would be 3 solar masses. So the only explanation that we have for that object that is that small, that we don't see, and that is that massive, is that the object there is a black hole. So that observation was in 1971, and it took something like 20 years to really decide whether that thing was a black hole or not. There was a famous bet between Hawking and one of his friends that he actually lost, because Hawking, most of the time, he loses his bets. And so that's the first example of a black hole. Okay, that's good. So now there is another system that has attracted a lot of attention that will bring us, and that will bring us to the second part of the Nobel Prize, which is the Galactic Center. So people have been noticing that if you point telescopes, so radio telescopes, towards the center of our galaxy, it seems that there is something really wild going on there. So people observed already in the 30s and more precise in the 70s that the center of our galaxy in the Sagittarius constellation hosts a really, really not bright, but really compact radio source. There is something that we don't see, but that emits stuff only in the radio frequencies. And it has been actually suspected for various reasons that I'm not going to enter into here now, but it has been suspected that that object was a black hole. And even more, it was suspected that at the center of every galaxy, there was a really super massive black hole. Okay, so that was just speculations. That was in the 70s. So some people decided, okay, well, people say there is a black hole at the center of the galaxy. Well, let's go have a look. Of course, they didn't go have a look by themselves. So these two people, Reinhard Genzel and Indra Ghez, they were actually leading observational teams that pointed arrays of telescopes at the center of the galaxy. And their goal was to observe individual stars going around in ellipses around the galactic center. So Genzel, he did this with the Very Large Telescope in Chile, and Ghez, she did this at the Keck Observatory in Hawaii. So this is what they did. So they observed stars, individual stars at the center of the galaxy. And they started in the mid-90s and they're still going on. So they have been working for almost 30 years at observing stars going at the galactic center. And this is the kind of thing that they are seeing. Here it does not appear really clearly, but if we zoom on the orbit of one particular star and follow the orbit, we see there is a star that follows some curve that we have already encountered, and that curve is an ellipse, and we don't see anything there. It seems to circle something that is black, and it has to be damn massive. So I'm telling you this like, oh, these people observe stars. I have to say that this is a super complicated and a very impressive task. Observationally, computationally, it is really hard to observe these stars individually. Imagine the center of the galaxy is at 26,000 light years away from us. The closest star that we see like a small dot in the sky, that's 4 light years. So these stars, they are observed, they are 26,000 light years. So it's a daunting task to observe these things, and it requires like a lot of ingenuity, patience, competence, and all these things. So we can also see more precisely, and we can model the orbits of all these stars around the galactic center, and this is what you would see. So these are simulations of stars going around a supermassive object at the center of the galaxy, and you see that all these objects, they go around in ellipses around something that we actually don't see, something that is dark. Now, what is nice is that we have Kepler's law, Kepler laws. So on the left, we see, okay, we have all the trajectories of a couple stars, so the nearest stars close to the galactic center. And again, we can see the trajectory, we can see the distance of the orbit, we can see the period of the stars. And from this, again, we can determine, we can have an evaluation of the mass of the massive object that lies at the center of the galaxy. And the mass of the massive object that is at the center of the galaxy is 4 million solar masses. So these people, they managed to figure out that at the center of our galaxy, there is an object that is completely dark, that is compactified in a really, confined to a really compact region, and that is 4 million solar masses. So the only explanation, the only reasonable explanation that we have for that object is that it has to be a black hole. So there's other observations that they did. So for example, remember that I told you that precise orbits around the black hole, they are not exactly ellipses. You know, the ellipse starts shifting at every period. For the closest star to the black hole, they were even able to observe that shift, that perihelion precession. So that's only after 1 year, and then they were able to observe this little shift here at the top. They were able to measure this, and the shift that they measured was exactly matched by the predictions of general relativity. And here we go. This is why they got the Nobel Prize. Genzel and Guest got the other half, they share the other half of the Nobel Prize for the discovery of a supermassive compact object at the center of our galaxy. So this is where we stand. I don't know how much time am I done, or I don't know. It's already
You're done.
late.
I mean, obviously, yes, you're quite done, but it was good to get to the end of it because we wouldn't have wanted to stop you.
So then, okay, because I have more to say, but maybe I will go fast on we can
carry on with the other evidence, although obviously I totally believe you. I find it extremely persuasive. Carry on.
But okay, so just you hear the words and you can ask me questions if you're interested. So there are other evidence. So that's the first evidence that, well, these are the evidence that we have so far that black holes exist. But recently, in the last 5 years, we got many more. The first one was gravitational waves. So I told you that once you have, so here I can show you a little picture.
Was in the form of gravitation.
So if you have two black holes that are spinning around each other, though these guys are a couple times the mass of the sun, and they are traveling, they're whirling around each other at almost the speed of light. So when doing this, they are actually perturbing the fabric of space-time itself. So they are like imprinting some like small wiggles in space-time. And these small wiggles, they are super, super small. It's incredibly difficult to measure them. But actually using an instrument that's called the LIGO, it's like two arms that are 4 kilometers each that are in the desert to avoid all background noise and everything. People were able to observe the little wiggles in space-time due to the fusion of these two black holes. And they observed like 18 events since September 2015, forming black holes between 18 and 142 solar masses black holes. So that's another, and again, all these results, all these observations are perfectly compatible with general relativity. And that what was the Nobel Prize in 2017. So now the other thing that you might have heard in April 2019, people managed to take a picture of a black hole. So that's the picture that you might have seen in the news. So that picture has been taken. That's a picture of a black hole that is 57 million light years away from us. So that's at the center of another galaxy. So observing that thing would be like looking at an apple standing on the moon. So it's again, so they had to build a telescope that was as big as the radius of the Earth to observe this. I'm not going to tell you here. So here I'm supposed to tell you what are we seeing. I'm not going to tell you. You can ask me, but I'm not going to tell you what we are seeing. But here it's a really special type of black hole that's actually a rotating black hole. So it's a rotating black hole. A rotating black hole drags a lot of matter with it, and that matter, like, it's really hot and there is a lot of friction. And what we are seeing is actually the disk around the black hole. That's the picture. I'm just going to skip this. So, is this the end of the story? So these works and these experiments show pretty convincingly that black holes, well, they are scary, they are really massive, nothing comes out of them, but we have to live with them. They are all around us in the universe. Probably there might be one in every and each of the 100 billion galaxies that are around us. And they give us a striking confirmation of Einstein's theory of general relativity. But now let me remind you, I mean, how did we arrive and how did Einstein arrive at general relativity? Well, he arrived at the theory it was just for philosophical questions. He was bothered by the fact that special relativity and Newton's laws were incompatible. And he arrived at general relativity, this idea that space-time is curved. Now, during this talk, there is a whole branch of theoretical physics that I haven't even touched upon. And that whole branch of theoretical physics. So here we have discussed about, planets, stars, the universe. So that's looking at physics at infinitesimally big scale, infinitely big scales, at large scales. But there's another branch of physics that describes the microscopic world, atomic and subatomic world. And so there is a whole story here that I'm adding with thermodynamics, electromagnetic, quantum mechanics, and quantum field theory. So quantum field theory culminated in the 50s where people worked out what is called standard model of particle physics, of which actually the last stone and the last verification was done really recently in 2013 by the observation of the Braut-Englert-Higgs boson that got François Englert and Peter Higgs the Nobel Prize. So the upper part of this diagram describes the subatomic world, microscopic world. And we know that if we want to describe the hydrogen atom, well, we need quantum mechanics, we need quantum field theory. Now, why am I telling you about this? It's because black holes, it's not the end of the story about black holes. So we have understood a lot of things about black holes, but there are a lot of open questions left. I'm just flashing them out. We can discuss them later if you want. What is the nature of the singularity? I mean, general relativity stops working there. Space-time ends, the laws of physics end, predictability ends. We don't have any physical theory that describes what happens at the singularity. Then there are two other really, really famous problems that are related to black holes. And they were essentially brought by Hawking and collaborators. The first one is the black hole entropy problem. So Hawking and Bekenstein noticed that actually black holes behave a little bit like, in ways, they behave like a thermodynamic system. They behave like a gas. Black holes actually have a temperature. Black holes have an entropy. The same way a gas can have a temperature, it can have an entropy. But for a gas, we know why a gas has an entropy. Well, an entropy of a gas is due to the fact that, there's a lot of molecules making up that gas, and the entropy will be just counting the number of configurations, giving you the same macroscopic aspects. If black holes have an entropy, then this raises the question, what are the atoms of a black hole? General relativity is not telling us anything about that question. And there is another question, there's a black hole information paradox that's related to the fact that if you throw stuff into the black hole, well, the black hole essentially is something that's pretty blind to anything you would throw in it. Maybe it's like somebody was mentioning Louise's bank account, or I don't remember. But you throw things in it, nothing comes out, and it's like all the information that you threw inside the black hole is actually lost. But losing information is actually in contradiction with quantum mechanics. So what does this tell us? Well, we have two theories that work pretty well. We have quantum field theory and we have general relativity, and they work amazingly well. And now guess what? These two theories are in contradiction. Isn't this amazing? It's great. And at the center of the contradiction, well, we have black holes. So we have learned a lot of things about black holes in the last 100 years. And these objects are strange. These objects are weird. They're mysterious. They take all information and we cannot get out of them. But we have learned a big deal about them. No, the story is really not over, and they have probably a lot of additional things to tell us. For example, if you want to unify quantum field theory with general relativity. So, whether we'll be able to unravel all the mysteries and the deepest mysteries about black holes and the nature of space and time, well, maybe we are just not smart enough. Maybe this is utopian. But in any case, this shouldn't prevent us from keeping walking and trying to find out. So thank you very much for your time.